Thank you. Thank you very much indeed for the organisers for the opportunity to speak, and also thank you very much indeed for organising such a fantastic conference. I think it's been a great success this week. I work for GeneSeq. We're a global provider of genotyping services. We work with breed associations, genetic evaluation providers, commercial companies and AI companies and the research community to provide genotypes across multi-species. What I'm going to talk to you today about is the evolution of cattle genomics and how that's led to the development of new genotyping technologies that we've heard about a lot this week. And then I'm going to talk about some new developments that we've been working on, where we've been taking those existing genotyping tools and trying to make them a little bit more flexible. And then I'm going to talk about give some conclusions at the end. So this slide just shows a timeline of the evolution of the development of cattle genomics. So starting in the early 90s, there were many SNPs that were discovered. Some SNPs associated with genetic recessive conditions like dumps and BLAD. Other SNPs that were explaining monogenic traits like coat color. And then SNPs that showed association to other phenotypes like milk quality and milk yield. During that same period, microsatellite markers were very widely used. Being used in parentage testing and also for whole genome scans and the detection of QTLs. And I would call this era a sort of a candidate gene era, where there were many single genes being discovered, QTLs being discovered, genetic recessives, and all of this information was being used for marker-assisted selection. Then in 2009, the publication of the cattle genome was released after many years of global collaboration. And this really has heralded a new era in cattle genomics, with such a lot of high-density information, new SNP information available, and that's facilitated the discovery of many other genetic conditions very rapidly. And of course, all of that SNP information has led to the development of new genotyping technologies. So those new genotyping technologies are things like the 50K SNP chip, which has really been the workhorse of genotyping across the research community, and has also now has been widely used for genotyping bulls and for the implementation of genomic breeding values. Around 2010, the high-density array was introduced, and that's been used again widely within research, and people talking about looking at using that for crossbreed prediction equations. Later on in 2010, the 3K chip was introduced, and that was designed as a lower-cost genotyping tool. The ability to genotype females, as we've heard a lot about this morning, and to be able to impute up to 50K to try to extract as much of the value of the 50K, but for a lower cost. That chip was kind of superseded by the 7K chip late last year, which is and the 7K chip, I guess, has been introduced as a more robust genotyping tool with more robust imputational capacity. All of these are excellent tools and are being widely used within the community. But what we thought was, we wondered whether there was an opportunity to try to make some of these tools a little bit more flexible. The problem we have is that our customer base consists of breed associations, genetic evaluation providers, commercial breeding organizations and AI companies, and of course the research community. And the sorts of tests that our customers require are several. And that includes things like parentage testing, genetic recessives, and genetic defect testing. And then, of course, they're doing a lot of genotyping on the chips I've just described, the HD, the 50K, the 7K, all for development of genomic breeding values. So that there's multiple applications, multiple tests, multiple sample submissions on multiple platforms. So what we're really trying to do is to find a solution to all of that by combining multiple tests onto one platform, with the objective of increasing the efficiency and reducing cost. So the idea would be that you can submit one sample and just have one shop, so that the ability to make more cost-effective genotyping and provide information back just on a single sample for ease of use for the customer. The opportunity to be able to do that arose by kind of the convergence of two pieces of information coming from Illumina. In early 2011, they announced their iSelect custom genotyping arrays, particularly with the ability to add on content to existing custom chips. And then later on in 2011, the introduction of the 7K chip, which provided, for the cattle community at least, an excellent platform on which to build. So what we've done is taken the combination of these two pieces of information to combine them into what we're now calling our new chip, the Genomic Profiler. So what have we done? Well, we've taken the basic 7K chip, and onto that we've added genetic recessive tests like arthrogryposis multiplex, fawn calf, things like coat color, parentage testing, milk quality, fertility markers, to make a bigger chip. And we've also taken the opportunity, because there was space on the chip, to be able to add some additional SNPs for it to aid imputation. So what's on there is the base 7K LD chips, SNPs. We've added some additional imputation SNPs. There are SNPs on there for SNP to microsatellite imputation, public recessive SNPs, and trait SNPs, and also added some royalty-bearing SNPs on there as well. So in terms of the imputation SNPs, there are a total of about 8,600 SNPs on there. That consists of the 6,909 SNPs that are present on the bovine LD array. With the help of USDA, who've chosen the SNPs, there are an additional 500 or so SNPs from the 3K array, about another 700 from the 50K SNP chip, and about 480 from the HD chip, and then 45 new markers. The objective of adding those additional markers was really to try to fill in some of the gaps on the 3 and 7K to ease the transition from 3 to 7K, and then possibly to look to see whether there was some gains in imputation accuracy that could be had, and possibly look to see whether it had increased utility in other breeds. So looking at the performance of the chips that are out there, the bovine and 3K and bovine LD chips is based on about 19,000 samples coming through the USDA, through their genetic evaluation program. And the GGP data, also through the USDA, is based on data going through their system since March this year. So you can see that the imputation accuracy comparing the 3K to the LD, there's approximately 4 to 5% increase in imputation accuracy. And the additional SNPs on the GGP chip add, on top of that, an extra 0.3% or so. That's in Holsteins. It's a similar story for Jersey and Brown Swiss. So Jersey's about 0.4% increase in imputation accuracy for between 3K and the 7K, and a little bit higher, about 0.5% increase in imputation accuracy with the additional SNPs that we have on the GGP chip. And on average, the reliabilities for the bovine LD, the 7K chip, are about 5% more than the 3K chip, and with the GGP chip, it's about 0.3% increase on top of the existing 7K chip. For parentage, there are 121 USDA parentage SNPs. They're already present on the original 7K chip. What we're doing as part of our reporting procedure when we're reporting results to customers is part of our masking and reporting procedures. We're able to pull out those SNPs and provide a parentage assignment if it's required. Additionally, on there, as I mentioned, there are SNPs for microsatellite imputation. Those have been developed by Matthew McClure at the USDA in Beltsville, and they're really designed for imputation of microsatellite alleles from SNP haplotype data. The proposal is that would be a very inexpensive and efficient way to transition from microsatellite to SNP-based parentage verification without having to genotype a generation of animals with both marker sets. And based on some early data and a personal communication from Dr. McClure, he suggests that he's observing the ability to impute microsatellite alleles for the ISAC recommended bovine parentage panel with about 98% accuracy across 4 breeds. So that's Holstein, Jersey, Brown Swiss, and Guernseys. In the majority of the cases, just a single haplotype is associated with one microsatellite allele, even across those 4 breeds. But in some cases, there are different alleles that are associated with different breeds. But he's working further to elucidate where some of these issues arise, and further work is underway to try to explain some of the anomalies that are seen in a few of those cases. In terms of recessive SNPs that are on the GGP chip, we have a list of public recessive SNPs and a list of royalty-bearing SNPs. So the public SNPs, it's possible to release the information on those SNPs without an additional charge. Royalty-bearing SNPs are licensed, and so additional charges have to be levied to pay the royalties for those markers. So in summary, the idea is one sample with multiple testing options. There's the base 6,900 LD SNPs on the chip, with an additional 1,700 imputation SNPs. There's 420 SNPs for microsatellite imputation, 23 public recessive SNPs and trait SNPs, and 9 royalty-bearing SNPs. And one of the features of working in this way is the ability to either genotype and gather all of that information in one go, or just pick and choose which bits of information you require from the chip. And then there's the option to reach back in time and get data on an animal after the sample submission and request genotype information after the event if required, because the data is already there in the database. So in terms of future developments, we're already working on a version 2 of the GGP chip, and that is going to have some additional add-on content for beef breeds, and we're adding many additional recessive genes for beef there. And we're also working on a higher density version. The 50K chip, there's about a third of SNPs are not informative in Holstein breeds, and we're looking possibly to develop a new higher density chip, which would take a combination of the 50K, a subset of 50K SNPs, the bovine 7K SNPs, and SNPs from the bovine HD to make a new 90K chip, The objectives here would be to make the chip more informative for beef, to make it more friendly towards Bos Indicus breeds, and then also have the ability, as I was describing with the other chip, to get recessives and traits all on the same chip. And there's a selection of people working with us on this, people like Tad Sonstergaard, Kurt Van Tassel, George Wiggins, Paul Van Reyden, Matthew McClure, John Beaver, and Dorian Garrick are all helping with the SNP selection for this new chip. So, in conclusion, cattle genomics has rapidly evolved over the last 15, 20 years or so, and it's been widely implemented in commercial breeding and in research. It's been used for genomic evaluation, parentage testing and identity, and the detection of recessive defects. The add-on capability that's now available for DNA chips has enabled us to develop a new tool to satisfy multiple testing requirements with just one sample submission. And we're working on further developments to try to enhance some of the higher density DNA chips. I'd like to just finish by acknowledging people that have worked with us on this. As I mentioned in the previous slide, Kurt, Tad, George Wiggins, Paul Van Reyden, Matthew McClure, John Beaver, and I apologize to Dorian Garrick. I've misplaced him as part of USDA. Of course, he should be at Iowa State University, so I apologize in advance for that. And my colleagues at GeneSeq, Daniel Pomp, Barry Simpson, and Jeremy Walker. Thanks very much for your attention. I'm happy to answer questions.